Hey everyone, thanks for coming to watch us talk. We're going to be talking about scaling Vault to your organization today. And I'm Brian Kassouf. I'm the Vault engineering lead for the Vault team.
And my name is Calvin, and I'm a software engineer also in the Vault team. Today, we're going to go through the journey of how your organization can go from having its first node and user to having a fleet of clusters with many users and services using Vault as their secrets management tool. Our journey begins with adoption and how we can get from 0 to 1. We break ground by setting up our physical storage, in this case, a simple 3-node console cluster. And separately, we spin up our first Vault server. And alongside that, we have a console client so that it's able to talk to our storage backend. We have our first developers and operators, essentially our early adopters, start experimenting with Vault, either via the CLI or the web UI. And as our adoption gets traction, we can scale up by turning our single Vault instance into a 3-node HA cluster. We also put a proxy in front of it. In this case, it's going to be an ELB. And at this point, not only are humans using Vault, but also instances and services. And that's about when we get into the expansion phase. With increased usage, we see issues such as permission management and performance degradation. We experience an increased number of leases, tokens, and policies, which means that permission isolation and delegation becomes hard. So the need for self-service arises. In order to mitigate this issue, teams naturally gravitate towards spinning up their own clusters. And this makes sense because it lets them retain control and decrease the number of leases, tokens, and policies, thus decreasing the overall server load. However, individual clusters do come with their own set of challenges. For one, they bring burden to developers, or now teams have to look for dedicated operators to see that, to watch the state of their Vault servers. They don't support replicated or shared data, which means that services that need to talk to different parts of the org now need to authenticate to these clusters separately. And they make it really complex for our SecOps team to oversee, since there's no centralized point to manage the state of the leases, the tokens, and the policies. So it's clear that there are two things that we need to tackle: management and performance. Today, we're going to first talk about two relatively new features that will help us ease management, and later down the road, Brian will go into how we can scale up and improve our performance. So let's go back to our organization for a moment and pretend that this is part of how it's laid out. We have ACME, which is our organization. And then below it, we have groups such as engineering, marketing. And then below those groups, we might have teams such as DevOps or front-end and so on and so forth. So what we want to do is let teams retain control of the data that they're allowed to access, but at the same time, give them the ability to grant other individuals, teams, or services access to that data if they desire. So how can we do that? The answer is Namespaces. Namespaces is a feature that was implemented in Vault 0.11 Enterprise, and it lets us isolate and scope access to data. You can think of it as vaults within Vault. And each namespace has its own set of secret engines and auth methods, its own identity store, and its own set of policies and tokens. And what this does is that it lets team essentially have control over the components in Vault. So if we were to apply our org chart into Vault, this is what it would look like. We have the root namespace, which is managed by the security team, and that's on by default. That's how we started using Vault. And then inside or below that, depending on how you look at it, we can have a namespace for our engineering org. And then inside or below that, we have another namespace, which is above engineering, for our DevOps team. So let's go ahead and create this in our actual Vault cluster. We can do so by easily issuing the namespace create command to first create our engineering namespace. And then underneath that, we create our DevOps namespace. And with these namespaces all set up, we then write our first policy in engineering called admin-eng using the engineering.html file. We'll go into what that file looks like in a minute. And for those of you who are less familiar with Vault, ACL policies basically lets us do allow or deny actions, or in this case, what we call capabilities, to certain paths within Vault. So if we go ahead and do a list of our policies, if we do it in the root namespace, we get back our default and root policies, which are available from the get-go. And if we do the same in the engineering namespace, we get back the admin eng policy that we've just written and a default policy, which is available right after namespace creation. OK, so let's take a look at that engineering.hcl file. In that file, we have two policies. So one powerful aspect of namespaces is constrained policies. This means that policies written to a namespace will only apply starting from that particular namespace. So to put it simply, a policy will have now the paths of those policies will be relative starting from the namespace in which they're written into. So as a concrete example, we have the first ACL policy, which is relative starting from sys/mount, but it applies to engineering/sys/mount star. And this policy, basically, what it allows us to do is list and CRUD operations for those paths and subpaths. And since namespaces can be nested, we can also do delegation. We can say that this policy, if attached to a token, can also reach into its child namespace. And this is what we're doing with our second policy by allowing basically tokens that are attached with the admin eng policy to do listing and reading under engineering/devops/sys/mount star. Cool. So let's go back to our command or to our terminal, and we issue our first token in the engineering namespace. And we also attach the admin eng policy into that. If we do a quick token lookup, we're able to see that this token has been created under the right namespace with the proper policies attached. And if we use that token to log in, we get back a successful response. But if we do a vault policy, a vault secrets list command, we get back a permission denied. And that is because the CLI by default will operate in the root namespace. And since we don't have permission to perform this action, we get back a 403. However, if we do a secrets list in the engineering namespace, we're able to get back our list of enabled secret engines. And that is because of our first ACL policy inside admin eng. And if we do the second command, which is the same, but under engineering/devops, we're also able to get back the list of enabled secret engines for that particular namespace. So one last thing that we want to do is do a secrets enable, which basically enables a secret engine. If we do that in the engineering namespace, we're able to get a successful response. But if we do the same thing now in engineering/devops, we get back a permission denied. And that is because we only have list and read capabilities for this particular namespace path. So if we go back to our org chart, we're able to mimic this particular layout in Vault with namespaces. And we can do so without breaking this tree structure into separate clusters. But more importantly, however, is that we don't lose the ability to oversee access and perform delegation. Now, the second thing that I want to talk about today is ACL templating, but not so fast. And that is because in order to fully grasp the power of ACL templating, we need to first understand the concept of identity. And there are two terms that come to mind when we're talking about identity. One is entities, which allows us to map a single user to 0 or more aliases. An alias can come from GitHub or LDAP or any of the auth methods. You can think of it as some sort of link between third-party services or authentication methods to a blob of info inside Vault. And similarly, we have an entity group, which can contain 0 or more of these entities as its member, as well as any subgroups. Cool, but how's this useful? Well, let's first take a look at the current state of things. Teams are using ACL policies through issued tokens to scope permissions. And some of the use cases that might pop up might be users who want to have their own workspace within the KV secret engine, or users who are logging in with the user pass auth method who want to update his or her own password. So for each of these cases, if we didn't have ACL templating, we would have to create a very specific policy for each of our users or groups or services. So as the number of entities increases and as the number of use cases that come up also increases, the number of policies that we mix and match also exponentially increases. So with a number of increased policies, as you can imagine, it can bring us all sorts of nightmares. So how can we improve the efficiency in managing these policies? Well, the answer to that is ACL templating, which is a Vault 011 OSS feature. We can address the first case, for instance, with the following ACL policy, which lets us give entities access to their own KV subpath. The beauty in ACL templating is that we can use the same policy and apply it to all the entities within the identity system. So we don't have to craft a specific policy for each user and manage the lifecycle of it, like the creation or deletion of these policies when the users get added or removed. So if our org has 10,000 users, for example, we can reduce 10,000 different policies down to just one. The second policy example that we have is quite long and barely readable, but trust me, if we don't have the ACL templating system, this would be next to impossible to replicate. And it does something that's very simple, which is to let entities from the user pass auth method update their own password. Without ACL templating, we would be either crafting a very broad ACL policy that would essentially allow a user to update the password of any other user, which is not ideal, to say the least. Or we would have to craft a very specific policy for each of our users in this particular auth method, which is not very scalable. And these are some of the other parameters that the ACL templating system provides. We can match entities by name, by ID, by mount accessors, or by metadata. And pretty much the same applies for groups. Cool, so with these two new features, we've been successfully able to ease management. We're able to give control back to teams through namespaces, and we get the ability to create flexible ACL policies through the ACL templating system. But as our org grows, so does our usage. And we eventually hit an inflection point that requires us to scale up our existing architecture and bump up our performance. So with that, I'm going to hand it off to Brian to tell us how we can do so.
Great. Yeah, so like Calvin was saying, as we onboard more teams and applications to Vault, their usage is going to go up. We're going to have to figure out how to scale Vault so that we can meet the needs of those applications and users. So today we're going to discuss scaling three kind of distinct operations within Vault. And it's important to break it out this way because they all use different types of features within Vault to scale. So first, we're going to talk about scaling write operations, scaling read operations, and then finally scaling authentications. So first off, before we jump into those three things, just want to cover some very general scaling advice. So here we have a pretty typical looking Vault cluster. It's got 3 Vault nodes. They're each talking to a console backend. And a single Vault cluster can actually scale pretty far. You just need to think through how to scale your storage backend up, because every Vault request, for the most part, will end up hitting the storage backend. And then additionally, scaling up your Vault nodes so they can handle more requests, more open files, and more memory. So let's talk through scaling write operations to Vault. And we define a write operation as anything that does end up resulting in a storage write to your storage backend. So if a request comes into Vault and it ends up doing an update or delete into console, then that's what we consider a write operation. And an important distinction for write operations is a shared versus a local write. And we'll touch more on this when we start talking about the next feature. But essentially, shared writes are things that are global to your whole Vault installation. So things like Vault configuration, such as what secret engines are enabled, what auth backends are enabled, and then the configuration for each of those. And then local writes are things that are specific to a single Vault cluster, things like leases and tokens, and data around dynamic secrets. So some common actions that applications might do that will result in one of these local rights is generating dynamic database credentials. So if you create a MySQL credential, that's a local right. Generating dynamic cloud credentials, generating PKI certificates, and so on. So the feature that enables this type of scaling are called replication or secondary clusters. Sorry. And they're a Vault Enterprise feature. They've been around for some time. I think they came out in Vault 07. And they allow us to provide horizontal scaling of read requests and the local rights. And it works by using inter-cluster replication. So it uses Vault's replication components to replicate data from a primary-secondary relationship. So if we add a couple secondary clusters, our architecture starts to look something like this. So we have a primary cluster and 2 secondary clusters. Each cluster has its own HA Vault setup. It has its own console cluster. And the primary will replicate shared data from the primary cluster to the secondary cluster. And so shared writes are always handled on the primary cluster. So again, things like Vault configuration, configuration for your storage backends, KV puts are all handled by the primary cluster and then replicated down to the secondaries. And that's just so that the secondaries can have the same configuration as the primary and be able to operate in the same way. And secondary clusters, as well as primary clusters, each have their own local storage. And so things like leases and tokens, data for dynamic secrets are able to be handled on each local secondary. And so each secondary is, each cluster is in charge of keeping track of its own credentials and revoking them when needed. And so this allows us to scale both read operations and those type of local rights. So next we're going to talk about scaling read operations within Vault. And so inversely to writes, a read operation is any type of operation that does not end up resulting in a write to the storage backend. So if a request comes into Vault and it only reads data, it doesn't end up changing or updating or deleting data in console. That's what we consider a read operation. And the interesting thing about these is it's not necessarily an HTTP GET method or a Vault CLI read. It could very well be a HTTP post or Vault write. And some common actions that applications might do that result in a read operation are getting data from the KV storage, doing a transit encrypt decrypt on some data, or signing and verifying it, signing SSH client keys. And so the interesting, we mentioned previously that secondary clusters enable scaling read operations, but it actually is a very heavy action to keep adding secondary clusters just so you can scale read operations. Because each secondary cluster needs its own console backend. It's generally designed to scale across data centers or across geos. And so we wanted to introduce a way that would allow us to scale these type of read operations within a single cluster. So that brings us to performance standbys, which was new in Vault 011, which was our previous release, and it's an enterprise feature. And performance standbys provide horizontal scaling of reads within a single cluster. And they, with performance standbys, write operations are still forwarded onto the active node. So the active node is still handling the write operations. Performance standbys handle the reads. And it works by using intra-cluster replication. So it uses the same replication components as secondary clusters, but it does not end up going to a separate console backend. All the nodes still talk to the same console backend. And performance standbys are elected similar to HA standbys. So here we have 4-node Vault cluster. Each of these nodes is talking to the same console backend. And typical HA all these nodes will come up. They'll talk to console. They'll all try to grab the leader lock. One of them will win, and it'll become active. And now the active node is going to handle all the requests. And if the active node is lost, one of the standbys can fail over and become active. And so this is generally a method of adding high availability to Vault. And so when the active node comes up, it'll write some data into console's encrypted storage. The standbys can read it. Inside that data is a TLS certificate that allows them to connect to the active node over a mutually authenticated TLS connection. And now the standbys will request forward all read and write requests to the active node. So in this setup, the active node is the only node handling any requests within the Vault cluster. And so performance standbys take this leader election to the next step. And now, after all the standbys connect into the active node will select a certain number of them to elect as performance standbys. And so we selected these bottom two. And so now we have one active node, two performance standby nodes, and one standby node. And the performance standby nodes now are able to handle read operations locally on that node, and they don't need to forward it onto the active node. So the writes are still handled by the active node. Reads are handled on each performance standbys. And if we lose the active node, any of these three nodes are able to come up and become active. And when that happens, a new performance standby leader election will happen and assign new performance standbys. Great. So now we have write operations, local write operations, and read operations scaling linearly. And the nice thing about performance standbys, is that as you add more performance standbys, you're able to linearly scale the amount of read operations that you can do. So the next thing we want to talk about is how to scale authentications. And so as you add more users and machines and applications to Vault, all of them will end up needing a Vault token before they can retrieve any secrets from Vault. And so it's just some very general advice around scaling your authentications is to reuse tokens where possible. And that just means that if a single user or a single machine is going to be accessing Vault over some period of time, it probably makes sense to keep that token around and reuse it versus re-authenticating every time you need to talk to Vault. Along the same lines, determining the appropriate TTLs for tokens and leases will take a lot of pressure off the storage backend, because if you only are using a token for about a minute or 30 minutes, it probably doesn't make sense to keep that token around inside Vault for 30 days. And so if we tune that TTL to be a little bit closer to the actual usage time of the token, it'll be cleaned up faster out of the storage backend and out of Vault's memory and allow new tokens to be able to take its place. And then the last bit of advice is to just use the appropriate token type for your use case. And so what are token types? And this is kind of a new concept, because up until today, there's only one type of token type. Service tokens are what we now call normal Vault tokens. And a normal Vault token is just, if you're familiar with Vault, what you know as the Vault token. And the service tokens have a number of features that make them really nice and flexible and meet a lot of the needs of applications. Service tokens can be renewed, so they have a default TTL. And if you extend that TTL, it'll extend the lifetime of the token. They can be revoked. So when you're done with the token, you can revoke it, and it's no longer able to be used. Additionally, you can add limited use counts to service tokens. So you can say this service token is only allowed to be used once, or this service token is only allowed to be used 5 times. And when those uses are up, the token will automatically be revoked. Service tokens are also tree-based, so they have a parent, and parents can have children, and those children can have children. And so when the parent is revoked, the entire tree is also revoked, so all the children and grandchildren. And it's a really easy way to manage a lot of tokens and like token sprawl and be able to revoke them just with one Vault command. Service tokens also have accessors, and an accessor is just an extra piece of information that's returned with the Vault token. And this accessor can look up the Vault token, and it can also revoke the Vault token, but it can't authenticate you to Vault, so it's inherently slightly less sensitive than the actual Vault token. Service tokens also have a nice feature called cubbyholes. And a cubbyhole is just an area of Vault storage that's set aside for this particular token. Only the token can write or read from it, and no other token can read another token's cubbyhole. So it's just an area of Vault that this token owns. And so because of all these features, creating a service token is actually a very heavy action. So if you think about it, we have to write the token value, we have to write the accessor value, we have to write the parent index, and potentially some cubbyhole data. And so right there, that's just 4 writes to the storage backend. And then we also have to clean up these tokens, so that's 4 more deletes to clean up all those things. If you're on enterprise, we're also writing wall entries for those. And so creating a lot of service tokens really explodes the number of writes that are happening inside your storage backend. But however, the nice thing about service tokens is because they're stored in the local type of storage, they are able to be scaled as we add more secondary clusters. So if you have 2 secondary clusters and you add a third, you now have 1/3 more capacity to create these service tokens. And additionally, because they're local storage, service tokens do not work across secondary clusters. So the secondary cluster that you create the token on, or the primary cluster, those tokens won't be able to use across those type of clusters. So batch tokens are a new feature in Vault 1.0, which came out today, and they are an open source feature. And batch tokens are designed to be extremely lightweight. They actually cause no persistence to storage at all. And they do that by taking the data we would have written into storage and instead encrypting it and returning it to the client. So it's a client-side only token. Vault has no knowledge of the token until it's handed it, and it can decrypt and verify the data inside of it. And so these type of tokens are not able to be renewed or revoked. Because they don't persist any data, they don't have a lot of the features of service tokens. So they aren't able to have child tokens. Batch tokens do have parents, and if the parent is revoked, then the batch token becomes invalid. They also are not able to have use counts, and they don't have accessors, and they don't have cubbyholes. So when you create a batch token and you use it to create a dynamic secret that results in a lease, the lease lifetime for that secret will be constrained to the lifetime of the batch token. So if the batch token is only good for 5 more minutes, your secret will also be cleaned up in 5 minutes. And you're able to configure roles or mounts within Vault to return this type of token. And so you can very granularly decide what user or application should be given a batch token and which user should be given a service token. And batch tokens are particularly useful for applications that have a short running time and will need to authenticate to Vault a lot. So Armand mentioned in the keynote that functions as a service is a great use case for this. If you have a Lambda job that needs a Vault token, it's only going to run for about a minute, and it's going to create a lot of these functions. It probably doesn't make sense to use a service token and create a lot of writes for just this short amount of time. So the nice thing about batch tokens is because they are not persisting any data, they're technically considered read operations. And so as we add more performance standbys, we can also linearly scale our ability to create batch tokens. So if we add 2 more standbys, we can create even more batch tokens. And then additionally, because the encryption keys that are used to create the batch tokens are replicated across secondary clusters, you're able to use batch tokens as long as they don't have a parent that is a service token. You're able to use them across clusters. So if you create a batch token on one of the secondaries, you can use it on other secondaries or on the primary. And that's another really nice feature that enables new workflows with batch tokens. So just to recap, now that we have changed our infrastructure a little bit and started using namespaces and ACL templates, we are better able to manage our teams. Our shared rights, such as KV and configuration, are still handled by the active node on the primary cluster due to the way replication works. But local rights are scaled per secondary cluster. Service tokens are also scaled per secondary cluster. Our reads are scaled as we add more performance standbys, and so are batch tokens. So that's all we had for you. Thank you so much. We'll be around after if you have questions. That's it. Thanks.